Okay, so in this lesson, we are returning to exponential functions. We first explored exponential functions in Math 1, and I'm sure that you've talked about things that grow and decay exponentially in other courses. Exponential functions are multiplicative. That's really important that you understand that. That's how we pick out behavior and that it's an exponential function. So what that means is when the input values are constant, there's a constant multiplicative change in the output. We can recognize an exponential function because the exponent contains the input variable x. All right, so let's look at a numerical example. If we look at this first example, the x values are increasing by 1, and also in this second example, the x values are increasing by 1. So that's what we mean by the input being constant. It's the output where we see the behavior. So looking at our first example, we can see that we go 3, 9, 27, 81, 243, 729. Well, what I recognize there is that to get from one term to the next term, we are multiplying by 3. So it's like this one's 3 to the first. This is 3 squared. This is 3 cubed. This is 3 to the fourth. This is 3 to the fifth, and then 3 to the sixth, because we multiply by another 3 each time. But if we look at this second example, 4, 8, 12, 16, 20. That one is increasing by 4 each time. So to get from one term to the next, we're just adding 4. Where in the first example, to get from one term to the next, we were multiplying by 3. Therefore, the first example is exponential. And the second example is not exponential. It actually happens to be linear because we're adding the same number over and over again. All right, so make sure you note that on your paper. The first one's exponential because it has that multiplier of 3. The second one's not exponential. It's actually linear because it adds 4. If we wanted to find the slope of the second one, we would say the change in y is 4, where the change in x is 1. So it would have that slope of 4 over 1. Looking back at the first one, if we wanted to write a function that would represent this, after you can see that's 3 to the first power, 3 to the second power, 3 to the third power. And if you notice, the exponents on these 3's match the input value. So the function that would describe this is y equals 3 to the x. All right, so let's look at this graphically. Graph each function on the coordinate plane and discuss key features, asymptote, domain, and range. And when we're doing this, the exponential parent graph is just y equals b to the x, where that base we can change. So in the first one, we're going to do a base of 2 and a base of 3. And the second one, we're going to do a base of 1/2 and a base of 1/3. Since it's been a while since you have graphed these exponential functions, I want to, by hand, go back through and look at how these behave and what they look like. So I've just made up a table of values, and we're just going to substitute some negative numbers and positive numbers into each function. So for this first one, we're looking at f of x is equal to 2 raised to the x. So guys, we're going to start right here at 0. 2 to the 0 power. Remember that anything raised to the 0 power is 1. So that would give us 1. 2 to the first power. That's just itself 2. 2 squared. That would give us 4. 2 cubed would give us 8. When we go to our negative input values, so that would be 2 to the negative 1, 2 to the negative 2, and so on. Remember, that means reciprocal of. So that really means 1 over 2 to the first, which would be 1/2. That means 1 over 2 squared, which would be 1/4. So this is going to be 1/2, 1/4, and then 1/8. So recall, anytime you raise a number to a negative exponent, it means the reciprocal of that number raised to that power. All right, so let's look at this graphically. So when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8, which would be way up here, and it's not going to fit on my graph paper. When x is negative 1, y is 1/2. X is negative 2, y is 1/4. X is negative 3, y is 1/8. I want you to think about this. If we continued going towards negative infinity, what would happen to our y values? So, for example, if I substitute negative 4, we'd be at 1 over 16. Negative 5, we'd be at 1 over 32. Then 1 over 64. Then 1 over 128. Then 1 out of 256. If you think about it, those, as x goes towards negative infinity, that y value is just going to keep getting smaller and smaller and smaller. And so it actually starts to converge towards 0. It gets closer and closer to 0, but it never actually gets there. So this graph looks like this. And that's why we call this an exponential growth, because as x goes towards infinity, y just takes off. It gets really, really big. But as x goes towards negative infinity, the y values get closer and closer to 0. So again, because this is increasing, we call it a growth or exponential growth. And I've just noted here, and you're probably going to put this in the notes, notice how as it goes towards negative infinity, as the x values go towards negative infinity, your exponential curve kind of planes out here. It's like it plateaus. It gets closer and closer to 0, but never actually equals 0. So what I would like for you to do now is I'd like for you to pause the video, and I want you to come up with the points for g of x on your own. Please do not use technology. Try to see if you can come up with those and graph it and see what it looks like. Pause now. All right, well, hopefully what you can see is the graphs look similar. They both have that increasing for the domain of all real numbers shape. They both have this curved shape. But as the base gets larger, so when we went from a base of 2 to a base of 3, once you get past that y-intercept, it curves up faster because it's growing faster. But before that, it's actually a little bit lower. The graphs, though, are very much the same. All right, let's look at this in Desmos real quick. I want y'all to see how you can explore this type of stuff in Desmos. So I've gone in Desmos, I've set up my graph, I've gone over here in my little wrench. I have cut off the minor grid lines and made the step for each one 1. I think that just gives you a clearer picture. And then I've come in here and I've typed in y equals 2 to the x. Something you can do in Desmos if you haven't learned this before is once you type something in, you can hit that little bolt, you can duplicate it, and you can create a table, and it'll show you some of the points on that graph that we had already come up with. I also want to add on here y equals 3 raised to the x, since that was our second graph. And I can do the same thing. I can come in here to this bolt, and I can duplicate it and then create a table to see the points on there. And you can see that those are the points that we should have come up with on our paper. And something else you can do in Desmos is click in the graph and pull it down so you can kind of look at it. We can see how that exponentially increases. It just takes off. That's why exponential functions are the fastest growing functions in the long run. They beat quadratic functions, cubic functions, all our power functions. They are our fastest growing. But you can also see that they plane out here at y equals 0. They get closer and closer to 0, but actually never get there. They're almost there, but never get there. All right, so let's talk about some important features of this graph. This graph has something very special called an asymptote, and you should have learned about asymptotes back in Math 1 when you learned your exponential functions. Because this graph converges to a particular y value as x goes to infinity, or if x went to, or as x goes to negative infinity, we say that it has an asymptote. I know that's a funny word, but it's a mathematical term. And the asymptote in this case is at y equals 0. So I'm just going to put that on there. Wherever your graph planes out at, that's your asymptote. Also, let's talk about the domain and range. Those are always important features of our graph. So for this graph, we have a domain of all real numbers because it covers every x value we can think of. Even though it looks like it's turning up and going straight up, it doesn't. It still keeps moving towards positive infinity on the x-axis. However, the range is 0 to infinity, not including 0, because remember, even though it gets closer and closer to 0, it never actually reaches 0. You'll also notice that both of these graphs have the same y-intercept. They both have a y-intercept right here at 0, 1, and that's because any number raised to the 0 power gives us 1. Okay, I would like for you, without using technology, try to create the table and the graphs of f of x and g of x when we change the base to be 1/2 and 1/3. And then after you've done it, check yourself with your technology. So go ahead and pause the video. So hopefully you can see when you do these that they're very similar to the first one, except for it's reversed. So when we raise 1/2, for example, to the -1 power, it does the reciprocal of, so it makes it 2 to the first, which is 2. When we raise 1/2 to the -2 power, it does 2 squared, which is 4. So it reverses them, and if we had to put these on the same axes, we would see that these the graph of y equals 2 to the x and the graph of y equals 1/2 to the x are pretty much a mirror image over the y-axis. One is the growth and one is the decay because they are reciprocals of each other. So if we look at these graphs, we can see that they are decreasing from left to right. So because they are decreasing, we call them a decay exponential function. So make sure you get that in your notes. It's decreasing. So this is an exponential decay. It also has an asymptote at y equals 0. They still plane out at y equals 0. So make sure you note that on there, that that's its asymptote. And they have a domain of all real numbers and a range from 0 to infinity, just like our growth graphs. They also have a y-intercept at 0, 1. Notice I have not talked about the x-intercept because neither one of these have an x-intercept because they never actually reach the x-axis. All right, so in general, what is an exponential function? An exponential function is a function of the form f of x equals a times b to the x, where a is a non-zero constant. We call a our initial value. It's kind of like your vertical stretch or shrink, but it can't be 0 because if it was 0, your whole function would just be 0. And the base must be greater than 0, but the base cannot equal 1. So let's talk about that. All right, so one of the restrictions for an exponential function is the base cannot equal 1. So I'm going to leave that a value at 1 right now. Here's why the base cannot equal 1. If you raise 1 to any power, it just gives you 1. So it would never grow or decay. So that's why the base can never equal 1. Now watch what happens. As I increase the base greater than 1, it grows. The bigger it is, so I'm going to come right here, like watch, from 2 to 3 to 4 to 5. The bigger the base is, the faster it'll grow in the long run. Another contingency is the base has to be greater than 0. Watch what happens when I go to the negatives. It just disappears. And that's because a negative number raised to a odd power is negative. A negative number raised to an even power is positive. So it's just all over the place. So that does not work. So I'm going to come right here and fix this slider so it only goes from 0. And then I'm going to put it to 10 so that we can see what happens. All right, so watch what happens when my base is a number between 0 and 1. The closer my base gets to 1, the closer it kind of is to the x-axis. It doesn't decay as fast. But the closer my base is to 0, the faster it decays. And it's kind of like that 1/3 versus 1/2 versus 1/4. But that's why we have those restrictions. The base always has to be a positive number, and it can never equal 1. It's going to be very important that you learn the formula y equals a times b to the x. Just like when you were back in 8th grade math and you had to learn y equals mx plus b, you need to learn this formula too. You should have learned it in Math 1. It's going to be extremely important for us to be able to write functions and to be able to solve problems, word problems, and modeling problems. All right, some characteristics of the exponential function. The function is continuous. That means there's no breaks in it. It's not like a piecewise function. You're not going to, if you draw an exponential function, you never pick up your pencil. And that's why the domain is all real numbers. The range is all positive numbers anytime a is greater than 0, and all negative numbers if a is less than 0. The reason for this part is because if you put a negative number in front of that base right there, it's going to reflect over the x-axis. And we've learned that from learning our transformations. So for our parent function, it's either all positive numbers or all negative numbers for our range. The x-axis is the asymptote, that y equals 0. And of course, this is before we start transforming it. The graph also contains the point 0a. The y-intercept is always going to be a. All right, let me explain that. For the graphs that we did above, the y-intercepts on all of them were 1, but that's because we never multiplied in front of the function by a number. Go back to the basic graph y equals 2 raised to the x. Notice as I change a from being 1, if I increase it, notice that whatever a becomes, That's what my new y-intercept is. And that's because you're stretching that graph vertically by a factor of that number. So if your y-intercept's normally 1, and I then multiply by 3, now my y-intercept's going to be 3. And that's why we call that the initial value of the function. If I make my y-intercept negative, for example, it flips the whole graph over because it reflects over the x-axis. But look how when I make it negative 3, my y-intercept is now at negative 3. All those transformations we've learned are going to apply here. All right, in the graph of y equals a times b to the x and y equals a times 1 over b to the x are reflections over the y-axis. And again, folks, that has to do with, look at the graphs that you have above. Look at y equals 2 to the x and y equals 1/2 to the x. Let me show you why that works algebraically. If we have y equals 2 to the x, and then we have y equals 1/2 to the x, using my exponent rules, 1/2 is equivalent to 2 to the negative 1. So that makes that y equals 2 to the negative x. Remember what we learned. Anytime you have a negative inside the function, it reflects over the y-axis. So you can see that y equals 2 to the x right here and y equals 2 to the negative x algebraically meet that transformation. All right, there are two types of exponential functions, and when I'm looking at this, I'm looking for when a is greater than 0. We have exponential growth, and exponential growth happens anytime the base is greater than 0. The base is greater than 1. And then we have exponential decay, and exponential decay happens anytime the base is a number between 0 and 1. You've got to know that, folks. Anytime your multiplier is greater than 1, it's going to grow. Anytime your multiplier is between 0 and 1, it will decay. All right, so for each of the following, what I would like for you to do is I would like for you to determine whether it's a growth or a decay, and also name the A value and the B value. Before you do that, I want you to take a few little notes on our basic formula. Remember, our basic formula is y equals a times b to the x, where a is always the initial value, and it's the y-intercept. Now, of course, anytime we shift this graph, if we were to add or subtract anywhere to this function, that y-intercept will no longer be a. It'll be a plus or minus whatever that shift is, and we'll see that in a little bit. B is what we call the base. It's what's being raised to the power, but it's also what does the multiplier. It's the behavior of the function. All right, so for each one, decide whether it's a growth or decay, and go ahead and state what A and B would be. Pause the video now. Look at the first two to make sure we're on the right track. The first one would be a decay. The base, the multiplier is 0.7. It's a number between 0 and 1. And that y-intercept or initial value would just be 1 because it's like there's a 1 right in front of here. The second one is a growth because the base, the actual multiplier, is 3. Don't let that 1/2 confuse you. That 1/2 is just that vertical shrink in front. But that would make the y-intercept 1/2. All right, try the next two. Okay, C is a growth because the multiplier is 4/3, and 4/3 is a number greater than 1. That y-intercept would be 10. Check out D. D, we want to, when we first look at it, I'm like, ooh, that's a decay. The multiplier is 1/2. But notice that it has a negative up in the x. So remember, if you have a negative inside the function, it reflects over the y-axis. So originally, if that negative wasn't there, it would be a decay. But when I reflect it over the y-axis, it's actually going to be a growth. And again, let me show you why that happens. That's really, if you have 1/2 to the negative x, that's really saying 1/2 to the negative 1 times x. Well, if I raise that 1/2 to the negative 1, that means the reciprocal of, so that becomes 2 raised to the x. And we know that 2 raised to the x is a growth. So technically, we could rewrite this as y equals 2 times 2 raised to the positive x by doing some algebra right there. So this one is a growth. The initial value, or the y-intercept, would be 2, and the multiplier, the base, is actually 2 in this case. Okay, so the last part of this, part 1 of this lesson, we're doing this lesson over 2 days, is to actually do these graphs. A lot of this is conceptual, but it's so important that we get this down pat. So for each of these, we want to describe the transformation and graph each function. State the asymptote, domain, and range. All right, so if I look at this very first one, it doesn't have any adding or subtracting in it, so we know we didn't shift it. But what we can see is that the y-intercept is at 3, because that's that initial value. And if you need to, you might want to write that at the top of your screen, your formula. Okay, so tomorrow in class, we will do the graphing part together. Hopefully you got the basics down. You may want to go ahead and on the next page, just write down this formula, y equals a times b to the x, where a is that y-intercept, that initial value, and b is that multiplier. And if you are working from home tomorrow, you're definitely going to want to live stream this class so that you can understand these graphs. And then after we do the graphs and those transformations on the next page, we'll do the first part of the practice together. The practice for this part is only going to be, when you go to the 3.1 assignment, is only going to be numbers 1 through 6.